Hello everyone. In this video lecture, let us discuss about the properties of Z transform and their proof. Right? To begin with, let me start with linearity property of Z transform. The linearity property of Z transform states that Z transform of a linear weighted combination of discrete time signal. Linear weighted combination of discrete time signal dt signals is actually denoted by a1 times of x1 of n plus a2 times of x2 of n. Linear weighted combination of discrete time signals. If you apply Z transform on it, the result will also be linear weighted combination of Z transform of individual signals. What does it mean? How will we prove it? Let me get into the property directly. When we calculate Z transform of a1 times of x1 of n plus a2 times of x2 of n, according to the formula, the signal for which you need to calculate Z transform multiplied by Z power minus n. When we expand this, we come to know that this can be expanded as summation n varies from minus infinity to plus infinity a1 times x1 of n Z power minus n plus summation n varies from minus infinity to plus infinity a2 times of x2 of n Z power minus n. So, Z transform of a1 times of weighted linear weighted combinations of discrete time signals is given by, according to the expansion, summation n varies from minus infinity to plus infinity a1 times of x1 of n Z power minus n plus summation. You can break it into two summations. So a to x2 of n Z power minus n. When we take the constants outside which are independent of time, a1 is taken outside, right? Summation n varies from minus infinity to plus infinity x1 times of Z power minus 1 plus a2 times of summation n varies from minus infinity to plus infinity x2 of n Z power minus n. So you can easily see that this is x1 of z is a transformation of x1 of n, where summation of x1 of n Z power minus n, where x2 of z is obtained by taking summation over minus infinity to plus infinity x2 of n into Z power minus n. That is denoted as x2 of z, isn't it? x1 of z and x2 of z, using which I can simply write the expression as a1 times of x1 of z plus a2 times x2 of z. So, Z transform of linear weighted combination of discrete time signals is equal to linear weighted combination of Z transform of individual discrete time sequences or signals. Second property, shifting property. What do you understand from shifting property? See, there are two cases. One is meant for two-sided general Z transform case, right? How will you represent this? The shifting property of Z transform states that Z transform of a shifted signal will also be shifted by m units of time by representing it by multiplying Z power m to the Z transform of the unshifted signal. For example, I have a signal x of n. When you apply Z transform, it becomes x of z. Everybody knows about it. Because of the shifting property of z transformation, if the signal is shifted by m units in time, it will get reflected in the form of z power minus m multiplied by x of z. Notice it. Or I'll write it in this way: z transform of x of n plus m, the signal is advanced by an amount of m units, will also be represented by multiplication of x of z. Original unshifted signal z transform is given by x of z. This is called z transform of unshifted original. Unshifted signal. I'll give it like this. So this will be represented as z power m into x of z. How to prove this? These are the statements given in the property. How to prove? Proof. I'll start with the definition of z transform of a double-sided sequence. Z transform of x of n is given by summation n varies from minus infinity to plus infinity x of n z power minus n. If you are asked to find out z transform of the signal which is shifted by m units in time, then according to the formula, n varies from minus infinity to plus infinity, the signal for which you are supposed to calculate the z transform should be written. Right? Now let me introduce a dummy variable n minus m is equal to, say, k, where n will be equal to k plus m. Agreed? When n is equal to minus infinity, this small k becomes, what will be the value? Minus infinity. Look at this equation. When n is equal to plus infinity, k becomes, small k becomes plus infinity. So using these intermediate substitutions, z transform of x of n minus m is going to be written as summation x of n minus m is replaced by, say for example, according to our substitutions, x of k, where k may be from minus infinity to plus infinity, z power minus n is replaced by k plus m. I'll write it in the next slide. Z transform of x of n minus m is given by z transformation, where the dummy variables or the temporary variables are substituted. So this will become x of k into z power minus of k plus m. You can notice that this becomes summation k varies from minus infinity to plus infinity. X of k is available, z power minus k is available, along with this z power minus m is also available in this expression, extra term. What should you do? Let me take this term outside the summation, because the summation is for k. Only the variables or the quantities which are functions of k can remain inside. Remaining variables can be taken outside. So based on which I just plan to take z power minus m outside. So the remaining expression will become k varies from minus infinity to plus infinity, x of k into z power minus k. Or I will put it in this way: z power minus m is available already. Just think about changing the temporary variables or variables in turn. Instead of k, if I use n, it becomes n varies from minus infinity to plus infinity, x of n into z power minus n. Simply k are all replaced by n. You can notice that this denotes z power minus m into x of z simply. This is what I told you at the beginning. Z transformation of a shifted sequence in a case of double-sided sequence becomes z power minus m into x of z. It is proven. This is for double-sided sequences. There is one more. One-sided, I'll mention about case 2. You will get one-sided is a transform. One-sided is a transform was also one of the cases inside. In such case, x of n might have been defined, for example, a value greater than or equal to 0 and less than or equal to infinity, like this, defined for values of n between 0 to infinity. In such cases, I'll straight away write the result. Z transform of x of n is equal to x of z, whereas Z transformation of x of n minus k delayed by an amount of k will be written as z power minus k into x of z. There is no doubt. Along with this, you will get an additional term where I varies from 1 to k, x of minus I z power minus of k minus I. Right? Alright. Z transform of x of n minus k is written as z power minus k into x of z. Z transform of the unshifted signal is multiplied by z power minus k. That's okay. Along with this, you will get an extra term where k is equal to, or I is equal to, I will put it like this, I is equal to variable which is not used so far. I is equal to 1 to k x of minus I z power minus of k minus I. This should be remembered, then only you can use this property for one-sided signals. One-sided signals. For one-sided signals, we need to think about, I can easily prove this also. How will I prove? When I have Z transformation of x of n minus m is equal to summation, yes, summation n varies from one-sided 0 to infinity, x of n minus m z power minus n is equal to summation n is equal to 0 to infinity. That you know, okay, but just multiply and divide by, or I will put it in this way, multiply by z power m and then multiply by z power minus m also. For example, I will write it like this, x of n minus m z power minus n into, just multiply by z power m also by z power minus m. At any moment this will get automatically cancelled. This is required only for a kind of producing a proof. Actually, for proving this property we require this. Z power minus m is taken outside, remaining terms are combined together. So summation n varies from 0 to infinity, x of n minus m z power minus, if minus is taken outside, n minus m. So this will remain inside, whereas z power minus m is taken outside. If you are clear about this, I can proceed further. How will I proceed? I should take some temporary variable, say for example k is equal to n minus m. When I take n is equal to 0, k will be equal to simply minus m. When n is equal to infinity, that I don't have to consult anybody because k is equal to plus infinity only. You can look at that, the integral, the limits of summations are from minus m to infinity, minus m to infinity. So n is equal to 0 to infinity will get changed into minus m to infinity. Is a transformation of x of n minus m in the case of single sided. What has been achieved so far? Z power minus m is produced. Now, so Z transform of x of n minus m is represented as Z power minus m, right, multiplied by summation. Now because of the substitution, this will become summation k varies from, you can see that k varies from minus m to plus infinity. minus m2, right, minus m2 plus infinity. What is available? X of n minus m is replaced by k z power, because you can see that z power n minus m is also replaced by z power minus k. If this is made clear, I think now we can break the summation into two parts. Summation from k is equal to 0 to infinity in one term, so that this will become x of k into z power minus k. Whereas the remaining all other terms, what are they? Z power minus m into summation k varies from minus m to minus 1. X of k into z power minus k can remain there. Now I just want to make it clear so that the z transform of x of n minus m for one-sided single-sided sequence will become z power minus m into summation k varies from 0 to infinity. X of k into z power minus k is the first term. The second term becomes z power minus m is available multiplied by, now we can notice the summation in, you know that the k range of values are in the negative range only. So if I take those minus signs inside the variables, now this can be written as 1 to m x of minus k and then z power plus k, correct, minus is put up inside, and k can be replaced by n also in the first, right, you can think about it, the first term, whereas k can be replaced by I in the second summation. Now you can notice that this will become z power minus m into summation n varies from 0 to infinity x of n into z power minus n plus z power minus m into summation I varies from 1 to m x of minus I z power, what is it? Z power I, right? And then you can think of even merging, or you can think of taking this z term inside, and alteration of the expression gives me z transform of x of n minus m becomes simply z power minus m into x of z, right, luckily. Whereas the second term, since the z outside, what was present outside the expression is taken inside, I varies from m 1 to m x of minus I into z power I is there. Now minus m is brought inside, so that this can be combined like this, m minus I. This is what we told you, that the shifting property of one-sided z transform for a delayed signal will be the same as that of double-sided z transform if x of I for I is equal to 1, right, x of minus I, if I is equal to 1 to m, say for example x of minus I from I is equal to 1 to m, if they are identical with, they are similar, or if they are all zeros, right, then the shifting property of one-sided z transform for a delayed signal will be the same as the double-sided z transform. So I'll put it in this way, right? So these are all important terms you must remember as far as the time shifting property is concerned. I'll go to the second or the third property, multiplication by small n is equal to differentiation of z transform in z domain. I have a sequence x of n. I just plan to apply z transform. I could see that the result is x of z, right? Alright, if we multiply this x of n by n, this will become n into x of n. If we apply z transform on the whole, the product, the result will be taking the Z transform of the original sequence, differentiating that in with respect to Z, also multiply the result by minus Z is the process to be carried out. I'll mention like this. What would you, can it be extended? Yes, it is possible. When I multiply a sequence x of n by, for example, n squared, n cube, n to the power 4, n to the power 5, or n to the power, say for example, m, it is possible for me to say minus z into d by dz of, minus z into d by dz of. You can just proceed. How many number of times you have taken? That many number of times you have to differentiate and multiply the differentiated version with respect to minus z. Minus z d by dz of x of z. Can you just understand this, or you want me to explain it further? I am ready to explain this. Z transform of, say, n squared x of n is available with me. How will you obtain? If you know the Z transform of x of n, better you take the differentiation of x of z, right? Not only once, you have to apply this differentiation twice. Why? Because you have got n squared. So twice Z transform of x of n is actually differentiated, multiplied by minus n. The result is to be differentiated with respect to z and multiplied by minus z. So Z transform of n cube x of n will be equal to minus z d by dz of minus z d by dz of minus z d by dz of x of z. It's over. Now you can notice that. This is applied first, multiplied by minus z. On the result, differentiation is applied once with respect to z, multiplied by z. The result is differentiated with respect to z once and multiplied by minus z. How to prove this property? It's a very important proof. How to prove this? The proof. I'll say Z transform of x of n is equal to, according to the formula, if it is a double-sided Z transformation, double-sided sequence, n varies from minus infinity to plus infinity, x of n into z power minus n. Right? So, when I am asked to find out the Z transformation of n into x of n, then what should I do? I have to take the formula. In the formula, in the place of x of n, I have n into x of n this time, z power minus n. Right? Now, multiply by z and z power minus 1. The same expression, multiply by z and multiplied by z power minus 1. At any moment you can cancel these two. Right? This is an extra. Multiply by z and z power minus 1. If this is okay, I think I can proceed further. But just imagining, I just reassemble the terms so that I'll get summation n varies from minus infinity to plus infinity. X of n, let that be the hero. At the beginning of this summation it is available. Now I just take n, the term n, right? N into z power minus n, z power minus 1, or z power, yes, minus 1. Right. What is available? Z power plus 1 is taken outside. Agree. It's a small arrangement. This is combined with these z terms. That's all. Whereas this is brought outside completely. Right? Now, just multiply by minus, multiply by minus and outside the expression as well as inside the expression, so that this will become minus z. Summation n varies from minus infinity to plus infinity, x of n into, right, minus n into z power minus n minus 1, minus n minus 1, minus n minus 1. So here just apply simple logic. D by dz of z power minus n. What would be the value? It is minus n into z power minus n minus 1. Isn't it? If this is available here, how can you replace this minus n into z power minus n minus 1? You can simply imagine that it is the result of differentiation of z power minus n. Right? Just think about that. This is replaced by z power minus n. The result is alone present here. So I can replace this. So let me conclude. Z transform of n into x of n is equal to, already have minus z outside, summation is there, n varies from minus infinity to plus infinity, x of n is there, minus n into z power minus n minus 1 is there. I just ask you to assume that this is the result of d by dz of z power minus n. What does it mean? Because it is minus n into z power minus n minus 1, isn't it? So think of replacing minus n z power minus n minus 1 by z d by dz of z power n. So when you take this will become minus z into summation n varies from minus infinity to plus infinity x of n into d by dz of z power minus n. Interchange the summation and differentiation. So interchange. So d by dz of interchange. D by dz of, you can notice that the summation and the differentiations are integrated as are interchanged. You will get x of n into z power minus n. Here you can see that summation n varies from minus infinity to plus infinity x of n z power minus n. What does it denote? This is simply x of z. So I can write this as minus z into d by dz of x of z. So whenever you take the z transform of a sequence multiplied by n will result in minus z multiplied by d by dz of x of z, the original, right? This is how it is proven. The next property, I'll say, what is the next property? The property is called the fourth property, multiplication by an exponential sequence. Multiplication by an exponential sequence. Exponential sequence. What do you mean by exponential sequence? It is denoted by a power n. How to perform? I have a sequence x of n. I apply z transform, which is denoted as x of z. It's a function of z. If this is known to you, then z transformation of a power n into x of n, a sequence multiplied by rising exponential or exponential sequence in general, will be simply x of this z will be replaced by a power minus 1 into z. A power minus 1 into z. Just look at the way in which z is replaced in the original z transformation. I will say again and again, if I have x of n, if I know z transform, if it is x of z, just take the sequence, multiply by a power n, then the z transform of this resultant sequence will be simply x of the same, but in the place of z you will have a power minus 1 into z. Right? I'll prove this. So easily we can prove this. Z transformation of x of n, as you all know, according to the formula in a double-sided z transformation, it is actually n varies from minus infinity to plus infinity, x of n into z power minus n. Right? Z transformation of a power n into x of n becomes, this is summation n varies from minus infinity to plus infinity, a power n into x of n is the sequence for which we need z transform. It is put up at the center. Right? Now, just imagine summation n varies from minus infinity to plus infinity, x of n is available, whereas you can simply combine these two terms. So this becomes, let me combine in a special way, so that a power n z power minus n. How to combine them, how to represent it in the modified format? I just ask you to apply a trick. so that it will resemble the original formula, so that a power minus 1 into z power 1, so that the whole power minus n can be put up, so that at any moment a power n z power minus n will appear. If you bring the power term inside the braces, it will become like this. So this will be as a whole represented as x of a power minus 1 z, a power minus 1 into z. Agreed? So this is called multiplication by an exponential sequence. Another property, very interesting and very useful, quickly we can complete, time reversal property. Fifth property, time reversal property. If I know the z transform of x of n and the result is denoted as x of z, suppose I apply z transformation on the folded sequence, then you will notice that the z transform will not be x of z, it will be x of z power minus 1. How to prove this? Proof is also very important. Proof. How will I prove this? Because z transform of x of minus n can be represented as summation, n varies from minus infinity to plus infinity. Now we can notice that you have to apply z transform for x of minus n this time. So the remaining term is z power minus n. Right? Alright. When we assume some intermediate variable, say for example k is equal to minus n. When n is equal to minus infinity, k becomes plus infinity. When n is equal to plus infinity, k becomes, you can notice that, isn't it? There will be a change. K becomes minus infinity. So the range remains the same, minus infinity to plus infinity. Minus infinity to plus infinity. So I'll just think of replacing this n by k, so that it will become k is equal to minus infinity to plus infinity. X of k, z power k will appear, isn't it? Let me write it now. Z transform of the folded sequence is equal to x of minus n summation k varies from minus infinity to plus infinity, x of k into z power, what is that? Z power k. You can see that because k is equal to minus n. So minus n is replaced by k, z power minus n is replaced by z power k. But I just ask you to use a trick so that it will look like the original formula. So that I'll write it like x of k, z power minus 1 whole power minus k. It's a small arrangement that we plan to apply. K is a variable. K can be even replaced by n also. As a whole, wherever k appears will be simply replaced by n. So it becomes x of n, z power minus 1 whole power minus n. You can notice that the formula will become at last not x of z, this time x of z power minus 1, since z power minus 1 whole power minus n is present. Okay, so if I have the sequence x of n and its z transform is known to me, for the folded version of the sequence I don't have to apply z transform, just take the z transform of the previous signal, original signal, and replace z by z power minus 1, z by z power minus 1. If this is known to you, I think we can proceed further to the next property. That property is called conjugation property. Conjugation property. How will you apply z transform for a conjugate version of the signal? I have a sequence x of n, discrete time sequence, for which I know that the z transform is denoted as x of z. Suddenly I am just asked to find out the z transformation of its complex conjugate version of it, for which I should take the original unshifted or unconjugated z transformation, and I have to apply conjugate on the whole, where z must also be conjugated. You can see there are two asterisks present in the result. Let me introduce the proof. How will you prove this? I'll just take the proof. The proof side, you can find out z transformation of x asterisk of n will be represented according to the formula as n varies from minus infinity to plus infinity. you can notice that this is x asterisk of n, for which I need to find out z transformation z power minus n is available, right? Now the summation n varies from minus infinity to plus infinity, x of n is available, okay, but you can notice that, right, if I take asterisk as a whole outside, what will happen? The asterisk, since the asterisk is taken outside, z term must also be conjugated, then only it will become z asterisk power minus. Agreed? So what would be the result? This can be treated as x of z asterisk whole power asterisk is present. That will be represented as x asterisk of z asterisk, right? The sequence is conjugated. You can see that the not only z transform is conjugated, also the variable z is replaced by conjugate z, right? X asterisk of z asterisk, right? What is the next property? A very simple property, but is an important property, in fact, convolution property. I'll say convolution is an important property because it is straight away applied in the system analysis. I have a sequence x1 of n, right, for which if I apply z transform, I just get x1 of z, right? Similarly, z transform of another sequence, say for example x2 of n is available with me, which will give me x2 of z, right? What is the z transform of, if you know this and the previous two expressions, what would be the z transform of x1 of n convolved with x2 of n? Very simple. How will you find out? According to convolution property of z transform, we have to take the z transform of the first sequence and we have to take the z transform of the second sequence, multiply them, you will get the result. You should first of all know what is x1 n convolved with x2 of n. x1 of n convolved with x2 of n in discrete time domain, it is represented as convolution in discrete time domain is actually represented by the formula dt convolution. M varies from minus infinity to plus infinity, x1 of m multiplied with x2 of n minus m, right? You have to keep this in mind. Let us start supporting this property with a proof. How will you prove this? Let me take z transform of x1 of n convolved with x2 of n, because you know that the summation n varies from, according to the formula, minus infinity to plus infinity, x1 of n convolved with x2 of n, right? Z power minus n is a formula. And you know what is the expansion of convolution of two sequences. This is given by summation n varies from minus infinity to plus infinity. According to the formula for convolution, m varies from minus infinity to plus infinity, x1 of m into x2 of n minus m, right? All right. Already you had z power minus n here in this expression. I have used it. So this is alone expressed like this. Using the equation for convolution, it is expanded. And I just advise you to multiply by z power m. Multiply by z power m and z power minus m. What would be the result? Z transform of x1 of n convolved with x2 of n will become simply summation n varies from minus infinity to plus infinity. You have the expression summation m varies from minus infinity to plus infinity, x1 of m into x2 of n minus m. Not only this, already in the expression you can see that there is an z power minus n term. Everything is available. What is extra? We just want you to multiply by z power m and z power minus m. So this will have minimum 3 z terms available inside. Let us combine some of the expressions, right, and rewrite. So this will become summation n varies from minus infinity to plus infinity, because this is for Z transformation. Interchange, that is also possible, right? Or let me keep m varies from minus infinity to plus infinity, x1 of m alone outside, and z power minus m is alone taken outside. Group them, x1 of m, summation. What is left out is n is equal to minus infinity to plus infinity, x2 of n minus m into z power minus of n minus m, because we have combined these two terms, right? All right, now let us make some substitutions. I'll keep the line at the beginning of the next slide. Z transform of x1 of n convolved with x2 of n will be represented as summation. M varies from minus infinity to plus infinity. X, what was really taken outside, x1 of m into z power minus m. They are already grouped. What is left out? Summation. N varies from minus infinity to plus infinity, x2 of n minus m into z power minus of n minus m. I just advise you to have a local substitution. Say for example, n minus m is considered to be, say for example, a variable p. When n is equal to minus infinity, you know that the p value will also be minus infinity. When n is equal to plus infinity, p will also become plus infinity. If you know these two items, you can find out summation. M varies from minus infinity to plus infinity, x1 of m z power minus m is available as usual, whereas the second term of this expression will become p varies from minus infinity to plus infinity, x2 of p into z power minus p. Surprisingly, this is equal to x1 of ez, whereas this is simply equal to x2 of ez. Wow, this can be represented as x1 of z into x2 of ez. That's what I say. Z transform of two sequences, the two in a convolved format, will be simply equal to x1 of z into x2 of z, product of two Z transforms. I'll put it in the simplest format. Whenever you want to know the result of convolution of two sequences in discrete time domain, you just do like this. Take the individual Z transforms, multiply them, and then apply inverse Z transformation on the product. Very important, which we may have to use in future. Okay. One more property, correlation property. What do you know about correlation of two sequences? Correlation of two sequences. For example, I have a sequence x1 of n, and I have another sequence, for example x2 of n. I just want to know whether these two sequences are correlated or not, for which I can apply a formula in discrete time domain. This is represented as Rx1 x2 of, for example, m is equal to summation m is equal to summation n varies from minus infinity to plus infinity. X of n is taken as such, whereas x1 of n is taken as such, whereas x2 of n will be delayed by m units, and the resultant delayed sequence is multiplied with x1 of n. Right? This is called the correlation property. Correlation. No, not the property of Z transform. I have simply told you only about how to calculate correlation between two sequences. I have sequence, for example, x of n with me, and I have another sequence y of n with me. If you ask me to find out whether they are related with each other or not, correlated or not, I have to find out correlation between those two sequences using Rx y of m. M denotes lag, and this formula says n varies from minus infinity to plus infinity, x of n multiplied by y of n minus m, y of n minus m. Right? You keep this in your memory. If required, we may have to use this. For example, if I know the Z transform of the sequence x of n is equal to x of z, and I have the z transform of y of n sequence, which is denoted as y of z, right? When you are asked to find out z transform of the correlated sequence r x y of m is equal to simply the product of x of z, not y of z. Simply z is replaced by z power minus 1 in y of z, x of z multiplied with y of z power minus 1. I'll prove this property. So I'll put it in this way. Whenever you need to find out the relationship between correlation between two sequences, simply take z transform of those two sequences, and in the second sequence simply replace z by z power minus 1, multiply them, and then apply inverse z transform on the product. You will get the result of correlation, amount of correlation between two sequences. So how will you prove this? I can just take the correlated sequence r x y of m. You know that the summation will be from m is equal to minus infinity to plus infinity, r x y of m z power minus m, right? Summation m varies from minus infinity to plus infinity, r x y. Just before few minutes only I told you how to calculate that. N varies from minus infinity to plus infinity. Take the first sequence as such, right? Second sequence is delayed by m units. That is the result of correlation, right? But in the formula I have z power minus m. As usual, the correlation is expanded. Multiply by z power n and z power minus m. Multiply right hand side of this expression by multiply by z power n and z power minus n will help me to reduce this into a compact format. So summation m varies from minus infinity to plus infinity. Within the braces I have n varies from minus infinity to plus infinity, x of n into y of n minus m. Z power minus m is available, whereas it is multiplied by z power n into z power minus n. Now it's your turn. What you should do? You have to group the terms and the summations are interchanged. Now you can find out that the summation becomes n is equal to minus infinity to plus infinity. Alright, x of n into z power minus n, let it be grouped on one side, whereas the second part will become m varies from minus infinity to plus infinity, y of n minus m z power. When you combine those two terms, you can notice that it is z power n minus m, right? I'll carry on this expression to the next slide. Z transform of r x y of m lag m is equal to summation. Just before few seconds I wrote it. N varies from minus infinity to plus infinity, x 1 of or x of n into z power minus n, whereas the second expression is alone written as m is equal to minus infinity to plus infinity, x of n minus m, y of n minus m, z power n minus m. Right? Alright. What should you do? Let n minus m is equal to, say for example, a dummy variable p, right? When n is equal to minus infinity, p becomes minus infinity. When n is equal to plus infinity, p becomes plus infinity. Everything is okay. When I substitute this into this expression, this will become n is equal to minus infinity to plus infinity, x of n into z power minus n. The first term of this expression remains the same, whereas the second term is alone made as p made is from minus infinity to plus infinity, y of p into z power p, or I will put it as z power minus 1 whole power minus p. So you can notice that these two terms can be represented by, the first one can be represented by x1 of z or x of z, whereas the second term can be written as y of not z power minus 1. That's all. That's what I say. The z transformation of result of correlation of two sequences is simply the product of Z transform of the first sequence and the Z transform product of the Z transform of the first sequence and the Z transform of the second sequence, whereas in the Z transform of the second sequence, Z and all are replaced by Z power minus 1. That's all. There is one more property, the last property. I'll mention about them. They are not properties, in fact, they are called as theorems. Theorems. Initial value theorem. I'll mention about it. Initial value theorem. As usual, there will be a final value theorem also. Let me imagine that the x of n is a single-sided sequence. That means x of n exists only from 0 to infinity. Okay? If Z transform of x of n, Z transform of x of n is computed, it is denoted as x of z. In such occasion, if you want to know the initial value of this sequence, you just take Z transform of the sequence and apply the limit. Z tends to become infinity. Z tends to become infinity. To be remembered, to know, to compute the first sample, how to calculate this. I'll prove this, I'll support with a proof, right? X of z is equal to, according to the formula, one-sided sequence. Be careful in using the limits. N varies from 0 to infinity, x of n into z power minus n. Expanding this will give me x of 0, z power 0, plus x of 1 into z power minus 1, plus x of 2 into z power minus 2. Yes, it goes on and on. Whereas x of z is simply, what is x of z? X of z is, can be represented as x of 0 plus x of 1 divided by z plus x of 2 divided by z squared. So on. Keeps on going. When you apply limit z tends to become infinity, x of z, you will notice limit z tends to become infinity. The sequence x of 0 plus x of 1 divided by z plus x of 2 divided by z squared plus x of 3 divided by z cube, etc. You will notice that the entire expression except x of 0, remaining all other terms will become simply zeros. It only, it survives. That's what I say. Limit z tends to infinity, x of z is equal to limit z tends to become infinity, x of 0. But you don't have any z term here on the right hand side, so this becomes x of 0. So initial value of a sequence is identified as limit z tends to become infinity, x of z. If you want to compute the first sample of a sequence, you don't have to strive hard or you don't have to strain much. Simply take the z transform and apply the condition limit z tends to become infinity. That gives me x of 0. That's how it is calculated. Whereas the proof of final value theorem is really very tough. I'll mention about it. Final value theorem. What does it mean? I have a sequence x of n and the sequence is a one-sided sequence. It is available from 0 to infinity alone. Only in the range of 0 to infinity. One-sided sequence. Causal sequence. And when I apply z transform on x of n, the resultant sequence is actually the power series expansion of the sequence z power minus 1 plus x of 1 into z power, x of 2 into z power minus 2, etc. So, final value of the sequence, how to calculate it? The final value, what do you mean by that? The final value is infinity, is equal to limit z, this time should tend to become 1, whereas x of z is taken and it is multiplied by 1 z power minus 1, x of z, right? Or in other books people would have mentioned like this, z tends to become 1, x of z is actually multiplied by 1 minus z divided by, it is z minus 1, isn't it? Z minus 1 divided by z. Final value of a sequence can be identified like this. To prove this, it's not very tough, but a lot of mathematical tricks are required to be applied here. Z transform of x of n is known to me, which is denoted as x of z. That is actually according to the formula summation n varies from 0 to infinity. Since the sequence is a single-sided sequence, x of n into z power minus n is available. Whereas z transform of x of n will, if it is x of n minus 1, x of n, right? How will you use this in the formula? Summation n varies from 0 to infinity. The z transformation is to be applied on x of n minus 1 minus x of n, for which you need to calculate z transform multiplied by z power minus n. Z power minus n. There are two terms, left hand side and right hand side. I just take this part, the left hand side alone. I expand this z transformation on x of n minus 1 separately according to the linearity property, minus z transformation of x of n alone separately, right? Z transformation of x of n minus 1, delayed term, so it will become z power minus 1 into x of z minus z transform of x of n is equal to, what is it, right? And that too, I have to use one more condition here, I forgot to mention it. Since it is a one-sided z transformation, it is not only z power minus 1 into x of z, plus I need to take all those pending terms, z power minus 1 is to be taken. And you know that this is actually minus x of z. So this can be represented as, how will you write it? This will be represented as, this will be expanded as x of minus 1 right, this is z power minus 1 x of z plus x of minus 1 minus x of z. So I can group some of the terms here, first and the last term. The first term, the remaining term could be put up in such a way that x of minus 1 plus 1, is it plus or minus? Plus z power minus 1 x of z. I'll write it in the next slide, please. What is it? Z transform of x of n minus 1 minus x of n was expressed as z power minus 1 x of z minus, plus according to a single-sided sequence. So x of minus 1 minus x of ez, right? When you take x of minus 1 as the first term, the remaining term will become z power minus 1 x of z minus x of z. Or if I take x of minus 1, minus is a common factor outside, then this will become 1 minus z power minus 1 into x of z. So this can be finally represented like this. The left hand side part is alone expressed like this. I just want to mention one more condition. Taking limit on z tends to become 1, this will be, I'll write it, limit z tends to become 1 if you apply the condition on x of minus 1 minus 1 minus z power minus 1 into x of z is available. So x of minus 1, z is not available in the first term, so minus limit z tends to become 1 minus z power minus 1 into x of z is available. This is all about left hand side part of the previous equation. This is considered to be LHS and this is considered as RHS. I have not done anything on the RHS part, so let me introduce what happens in the RHS side. RHS becomes summation n varies from 0 to infinity x of n, or what is it, x of n minus 1 minus x of n multiplied by z power minus n. So take limit limit z tends to become 1. In this case also, limit, apply the limit z tends to become 1. This will be summation n is equal to 0 to infinity x of n minus 1 minus x of n z power minus n. All right. Limit z tends to become 1. So z tends to become 1. So you have to forget about this part. So this summation will simply be reduced as summation n is equal to 0 to infinity x of n minus 1 minus x of n. Correct? That's all. So applying the limit z tends to become 1, the term z power minus n becomes unity. This becomes unity. So now you can change the summation index from 0 to p and then apply the limit p tends to become infinity. Limit p tends to become infinity. The summation, small adjustment, instead of n varies from 0 to infinity, I say n varies from 0 to p. See, you can see that now it is only limit 0 to infinity only, n varies from 0 to infinity only. So this expression is x of n minus 1 minus x of n. When you expand this portion, this is simply limit p tends to become infinity, the summation n varies from 0 to p x of n minus 1 minus x of n. How to expand it? When you expand this, this becomes limit p tends to become infinity remains same, but you can notice that the first one, when n is equal to 0, x of minus 1 minus x of 0. When n is equal to 1, this becomes x of 0 minus x of 1. Right? Whenever n is equal to 2, then the next term will become x of 1 minus x of 2. Correct? I am trying to apply the limits for n everywhere, etc. It goes on and on. Suddenly one instant you will find out x of p minus 2, x of p minus 1, and is x of p minus 1. It's one group, whereas the last group will become x of p minus 1, p minus 1 minus x of p. If you cancel out, you can see x of 0, x of 0, x of 1, x of 1, x of 2, x of 2, x of p minus 1, x of p minus 2, something like that. If you cancel all the terms, the result will be simply limit p tends to become infinity, x of minus 1 minus x of p. Yes, available. This is, or I can even expand this as x of minus 1 minus x of infinity. This is all about RHS part. Don't forget, there are two parts now. Left hand side LHS is expanded like this, whereas RHS, right, LHS is mentioned like this, RHS is modified, at last you can see that it has become like this. So LHS and RHS, if you equate x of minus 1 minus limit z tends to become 1 minus z power minus 1, x of z is available on one side, whereas another part of the equation, x of 1 or minus 1, x of infinity is available on the other side. If you rearrange, x of infinity is equal to, you can see that these two terms will get cancelled. X of infinity is equal to limit z tends to become 1 minus z power minus 1 into x of z. This is what mentioned as the method to find out the final value of a sequence. If you want to know the final value of the sequence, you have to simply take the z transform of the sequence, multiply it by 1 minus z power minus 1 and apply the limit z tends to become 1. You will see that the result will give you the final value of the sequence. final value of the sequence. Thank you so much. Two more properties yet to be covered. One is called parsevals theorem. Yes, it is a tedious one. Already the video is running out of 1 hour. So I think it is essential that I have to put it up as part 2. Till then, I'll say goodbye. If you have any doubts about all the properties, you can feel free to contact me. So these are all the properties which I have mentioned: correlation, convolution, multiplication by exponential, or the properties like time shifting, linearity, conjugation, time reversal. All those properties we told you, and the differentiation in Z domain, multiplication by n. All those variables we have discussed, and the time delayed sequences and its Z transform, including linearity. These are all the properties we have seen so far. Thank you so much for patiently listening to me. Thank you.